Okay, my students, here we are preparing for your exam tomorrow. So let's talk about the things that you should know how to do before then. Okay, so some questions, like what must be true for a graph to be continuous at some value A? Okay, so I'm going to make a graph of this before we write the words. But if we have some axes and we're picking out some x value and we're calling that value A. Okay, if the graph is going to be continuous at that point, then some things have to happen. Number one, there needs to be a y value there, right? It has to exist. There has to be a point where f of a actually is there, right? It has to exist. And then from the right side, actually from the left side, as x approaches a from the left, right? So we write that as x approaches a from the left side, right? That needs to be equal to the y value there. So the y value at that point needs to be equal to the y value from this side, okay, as x approaches a from the right. So the little plus up there means from the right. The minus means approaching from the left. So we go for the graph towards here, and we come from this way, and something has to be there for them to meet at, okay? Those three things have to be there in order for your graph to be continuous. So the y value from the left equals the y value from the right equals the y value at the point. So maybe that's a good way to say it. The y value from the left equals the y value from the right equals the y value at A, right? From the left of A, from the right of A, equals the y value at A. So all three of those things come out to have the same y value. Now, remember, this is only going to happen with a piecewise function, okay? And so we'll talk about how we do this in a second, but this is happening with a piecewise function at your constraint. So we're worried about what's happening at -1, right? Because both of these equations have a -1. And we're worried about what's happening at +2. So that's where we're going to have discontinuities potentially, is at the constraints of your piecewise domains. Let's go back up here. What if we have a jump discontinuity? Okay, so graphically speaking, a jump discontinuity, okay, is where one y value is here from the graph on the left, and the other y value is somewhere else from the right. Okay? There's this jump in between your two y values at your x value of A. Right? So we have two different y values. And that's what we're going to say if we have a jump discontinuity, is that the y value from the left does not equal the y value from the right. And our other point, or other type of discontinuity, is a point discontinuity. So if we have a point discontinuity on the graph, that means that the left side comes to some y value and the right side comes to that same y value, but there is not an actual y value there. Okay, there's a hole, or that's a point discontinuity. So the y value from the left does equal the y value from the right. But, right, the exact y value does not exist. Okay, and we'll see what that looks like here in a minute from our from your piecewise function. So let's apply that to our actual piecewise function. It says describe the continuity at each domain constraint. Okay, so once again, I have highlighted the constraints. If we were going to make a quick sketch of this, right, we'll put some axes on here. We're looking at what's happening at -1. So this is one of your domain constraints. And we're looking at what's happening at +2. Okay, so it's kind of important to know on the left side of -1, we are graphing this. So we have a 2x plus 4 on the left side. In the middle, we have x squared minus 1. And on the right side of +2, we have -1/2 x plus 4. Okay, so it might help you if you actually write down this situation and put the equations in the places where we are looking to graph them, right, based upon their constraints. To the left of -1, we are doing this equation. In between -1 and +2, we're doing that equation. And to the right of +2, we're doing this. Okay, so what's happening here at -1? Right? Are the graphs approaching the same thing? So what you want to do is you want to plug in -1 into your equation. Okay? Plug -1 in there and see what the y value is from that equation when x equals -1. In fact, we're going to plug it into both of these equations, okay? Because both of these equations have something to do with -1. The linear is on the left side and the quadratic is on the right. So go -1 into both of those and see what we get. So this is what we calculate. When you plug -1 in, we get a y value of +2. So you plot that on here with an open circle because it says less than. Less than means open. And when you plug it into your quadratic, we get 0 as the answer. So we're looking at the y values. Is 2 equal to 0? And hopefully you know that it's not. Our graph, right, would look like something like this. So here's your 2x plus 4 graph. It's a linear. Your quadratic would look something like this-ish. Right? So there's a gap here. And what kind of a gap is there? Well, it's a pretty big gap. So what we're going to write is there is a jump discontinuity at x equals -1. Okay? Because one y value is +2, the other y value is 0, so there is a large jump in your y values at x equals -1. So what is happening at the other constraint? So at +2. So for that, you're going to plug +2 into these equations. Right, the ones on the left and the right side. So we're going to plug a 2 into your quadratic, and we're going to plug a 2 into your purple one. I guess it's a linear. Okay, so plug 2 in there and see what you get. So when I plug 2 into both of these equations, I get a y value of 3 from the left. 4 minus 1 is 3. And I get a y value of 3 from the right. A -half of 2 is -1. -1 plus 4 is 3. So I do get the same from the left side and the right side. But if we look at your constraints, this one says less than 2, and this one says greater than 2. Okay, so this is going to be your clue to know that there is no y value exactly at x equals 2. It has to have an or equal to in order for that y value to exist. Right, so every time we have a greater than, we have an open circle. And we have a closed circle when it's or equal to. So if you don't have an or equal to at that constraint, that's going to tell you pretty much that it's not going to be continuous. In fact, because the left side equals the right side, but there's not one there, not an actual point, this is a point discontinuity at x equals 2. Okay, so that's the process of deciding. You have to plug in those numbers. Plug in the number to the left, so using 2 equations, okay, the top and the middle, and then the middle and the bottom, and see if those y values give you the same thing. For point discontinuity, for jump discontinuity, or if all 3 of them are there, then that's normal continuity. Okay, what else we got? How would you explain that a graph or a function or a table is even? Okay, so these are our 3 different types of representations: a graph, a function, and a table. Okay, so for a graph, we're looking at the symmetry. A graph has y-axis symmetry if it is an even function. Okay, so what you're looking for is something that is centered on the y-axis, where the left side and the right side match up perfectly. Okay, an even function has y-axis symmetry. Okay, as a function, if you replace x with -x, and you get the same thing as you started with, right? The original function. That is the functional definition or the algebraic definition of an even function. Okay, so be able to recognize that this notation is talking about even functions. All even functions have that as their notation. Replacing x with a negative x does not affect your equation. Okay, these two equations are equal. And lastly, from a table, you'll notice from a table that every point you have, every point, so every x comma y that you have will change into a corresponding negative x comma y. Okay, so for an even function, the x values go from positive to negative, right? They change signs, but the y values do not. Okay, so if you're looking for a numerical explanation, that is your numerical explanation, that the x values change signs and the corresponding y values do not. So what about odd? Right? Our next thing is about odd functions. Well, we have a graph about the odds. We have a function about the odds. And we have a table about the odds. We'll get to that in a second. So a graph, you have origin or rotational symmetry. Okay, you can use either one of those words you want to, or both if you want. Okay, so it always goes through the origin. If your graph doesn't go through the origin, then it can't have origin symmetry, period. Okay, a function. If it's a function, then replacing x as a negative is the same as making your entire equation negative. Okay, and we have some practice on this review about how to do that, okay, how to tell. So that is the numerical, not the numerical, that is your function, your algebraic way that you can tell if something is odd. And then from a table, the numerical way, every point that we have turns opposite. So the x's are the opposite and the y's are the opposite. That's how we know that we have a origin symmetry or an odd function. Right? So if this point over here were 3, 1, then his friend point over here would be -3, -1. Right? Both x and y's change signs in an odd function. Okay. Next one. How do you decide if something is 1-to-1? Okay. So 1-to-1 means that every y value comes from exactly one x value. And every x value, of course, gives you only one y value. So from a graph, we're going to apply the horizontal line test. Which simply means you're going to draw a horizontal line through your graph. Okay, however the graph may be. It could be a crazy graph. It could be a non-crazy graph. Whatever. Okay, if you apply the horizontal line test and anywhere on the graph crosses more than once, that means this is not a 1-to-1 function. Okay, that's all it tells you, is that the function is not 1-to-1. If it fails the horizontal line test, then it is not a 1-to-1 function. Okay, from a table, we are looking at all the y values. The y values have to be different in a table. If all the y values are different, are unique, right? There are no repeated y values, then that table is a table full of a 1-to-1 function. So if any of the y values are repeating, then you do not have a 1-to-1 function. Okay, and what are the implications if it's not 1-to-1? That means that the inverse of your function does not exist. Okay, so that is why we do the 1-to-1 test, to see if the inverse does not exist. The inverse does not exist. So this graph would not have an inverse that exists. It is not invertible. Okay, so that's why we care about 1-to-1, because not all functions have inverses. Because if it fails the horizontal line test, that means we have one x value with two y values, and that can't happen. Okay, and then the last thing on this page is be sure to be able to write an absolute value function as a piecewise. Okay, and when there's a practice problem at the end of video number 3 for this review that helps you practice doing that. Okay, so these are the basics, right? This is your understanding of our concepts that we are being tested on soon. Hopefully that helps, and we'll see you in class. Okay, bye.